It's fine. All right. So the law of large numbers, just as our review, as the number of trials of a random event increases, the difference between what we expect to see and what we actually see approaches 0. So that was where we had talked about, like, with you flipping a coin, like, if you flipped a coin, I don't know why this is so blurry. If you flipped a coin, like, 10 times, you probably aren't going to get 5 heads and 5 tails. Like, yes, statistically we should, but that just usually doesn't happen. But if I flipped it 1,000 times, I'm probably going to get a lot closer to 500 heads and 500 tails by the end of it. All right, so the first example, commercial airplanes have an excellent safety record. Nevertheless, there are crashes occasionally with a loss of many lives. In the weeks following a crash, airlines often report a drop in the number of passengers, probably because people are afraid to risk flying. A travel agent suggests that since the law of averages makes it highly unlikely to have 2 plane crashes within a few weeks of each other, flying soon after a crash is the safest time. What do you think? Seeing if y'all remember what we talked about the other day. Chris gets a pass. Virginia doesn't.
I don't remember what you guys talked about the other day, but I remember this from last.
You don't remember from the other day, but you remember it from a year
Like
ago.
a whole year ago.
Yeah, because I wasn't really paying attention the other day.
Fair enough. What do we say about this phrase right here?
It's a
Fallacy?
fallacy.
There's no such thing as the law of averages. It's a trick question.
So it is a fallacy.
Yes.
But not how it originally said.
She said fallacy.
I thought that's what it was, because, like, it's false. I wouldn't say false,
That actually makes sense.
right?
Hey, Virginia,
Huh?
didn't you say Wallace
They are misusing, yes she did.
Trees.
They are misusing LLN, the law of large numbers. The law of large numbers only applies to large numbers of trials. Like long term, not short term. So then kind of on the flip side, this is the one more so that we talked about the other day, but if the airline industry proudly announces it set a new record for the longest period of safe flights, would you be reluctant to fly? Are the airlines due to have a crash?
No, because it's still part of like the same thing we're talking about in A.
Yeah. Basically, the probability is independent, so like one plane crashing has no effect on the next one crashing.
Unless they crash into each other.
Well, if that happens, something drastically went wrong.
How do you mess up that bad? I don't think. Has a plane crashed into each other before? Like just the regular like airline flight?
In the air, probably
Yeah.
not.
Yeah, I wouldn't think so.
Not intentionally. I mean, well,
Oh yeah.
airlines. Military planes,
Yeah,
probably.
definitely. I've still never actually used like an airport before.
You've never been to a airport?
Well, I've been to one, but like I've never actually like taken a.
Like you haven't
Like,
flown?
yeah, I've flown in a plane before, but it was like our friend's plane, and it
Oh.
was like
Yeah,
my
that's
uncle's
fair.
plane. My uncle has a plane.
I remember my favorite part about flying on the plane, the turbulence.
Yes.
Bro, I got so motion sick one time on a super turbulent flight. But I don't get sick on like daytime turbulent flights, only on overnight turbulent flights.
Do you know why that is?
So I have this like hypothesis as to why. So I had flown like many times. Well, I say many times. I have flown a lot now, but when I was little, we had to fly to Louisiana for a wedding, like a super quick like thing. And I was freaked out about flying. I was just like, all right, like whatever. Well, anyways, when we would like drive and stuff, I would never get motion sick. I mean, I was fine on that flight. But anyway, so it was like a gap of time before I flew again. Well, then in high school, we flew like a decent amount, like back and forth to Louisiana because my grandpa was super sick. And then, like we went on a family vacation to Yellowstone, so we had to like fly out there. And then right after I got back from Yellowstone, I went on a mission trip to Brazil. So I had flown like a decent amount in there, never gotten sick. Went to Brazil, and we had an overnight flight, which the overnight flight down to Brazil was totally fine. Wasn't turbulent. The way back, though, I started to not feel good, like, at all. Like, 2 hours left in the flight, and it was, like, a 10-hour flight. Because the plane was, like, doing this,
Yeah.
and I had been sleeping. So then, a couple years later, my family went to the West Coast for a trip, like to Oregon and like all of that, which we did again this summer. But our one flight was overnight, like a red-eye flight back. So like we left there at like 10 p.m. and we landed here at like 8 a.m. or something. Well, when we landed here, I felt like super sick. And like to the point that like we were all going to eat breakfast because it was obviously time to eat, and I like couldn't eat because I was so like I just didn't feel good. Like I never actually like got sick, but I just felt super sick. And then 3 years ago, we went offshore fishing at like out of Oregon Inlet down at the Outer Banks, and we had taken Dramamine and everything. I just think Dramamine doesn't really work for me anyways. And I slept on the way out because, I mean, it was like 4 a.m. Like, you get on the charter boats at like 4 a.m. and then you get out there to fish by like 5:30 or 6. Well, I woke up and I felt super sick. I actually did get sick, but I think also like just the boat in general. So my theory is if I sleep on something that's very turbulent, that's when I get sick or feel sick.
So if you're like wide awake the whole time, you think you'd be fine.
Yeah. I think it's like
That
just
makes
something with like the like all the whatever like in your brain and then like also in your stomach, and I don't know. I haven't figured it out, but that is the only thing. That is the only rhyme or reason, because it's when it's been like something like overnight or something like during a time when you like normally would be in bed asleep that I've had that happen.
Yeah.
Knock on wood, it hasn't happened any other times, but I don't know. Yeah, it's just a little stressful, but but yeah, so I try to avoid those overnight flights now if I can, because I just, it's like hours. I'm just like, ugh.
I feel like that would like mess up my day when I got home. Like if I got home really early, I wouldn't be using that day.
Yeah. I was concerned when we just flew back from the West Coast this year that I was going to kind of have a similar thing because we got back like super late at night, but fortunately it was fine. I think it's because I just normally stay up late anyways, and we had been on West Coast time, so it was only like 6 o'clock by the time we got home, like when it was there, but here it was like 10 or 11 at night. All right, I'm going to add option D on here, and then we'll read this problem because I don't want to forget to add this one. So option D is 0.40, this one's 0.30, 0.20, and 0.10. All right, well, this problem is going to kind of be interesting because next Friday, JCPenney often does something like this. I don't know if they're doing it this year on Black Friday, but normally they do. But many stores run secret sales, which is where you receive a like scratch off ticket. Sometimes when you walk in, sometimes when you get to the checkout and you get to like wipe it off or whatever, scratch it and see if what your discount is. And so the store has to tell like in advance, like, well, I don't know if they have to tell the public this, but this store particularly has to reveal the distribution of discounts available. Which of these probability assignments are legitimate? Okay, so basically this is like a multiple choice question. I'm just written in a table so it's easier to see. So A is basically 10% off is 0.2, 20% is 0.2, 30% is 0.2, and 50% is 0.2. Does this one make sense?
No, because it has to add up to 100, right?
Yep. At 100 if you're thinking about it as percent, or 1 if you're thinking about it as a decimal.
So then it's D.
So this one is less than 1, so this one is no. This one here is over 1, so B is greater than 1, so that's also no. Now, the catch though is with C, we have 0.75 plus 0.25 plus 0.25, so that puts us at 1.25, but minus 0.25, doesn't that also put us at 1?
Yeah, but like, would you be giving out negative discounts? Like, would negative people be?
Correct.
Yeah.
That's what I'm trying to, yeah. You can have a negative probability. So this is a negative probability, which is a problem, so no. This last one is exactly equal to 1. So that one would be our option. So basically, option D is what we would need there. All right, example 3, getting into a little bit more with the actual doing math. In a large introductory to statistics lecture hall, the professor reports that 55% of students enrolled have never taken calculus, 32% have only taken 1 semester of calculus, and the rest have taken at least 2 semesters of calculus. What is the probability that you choose a partner who has studied? And then it's going to be each of these options. So I'm just going to make a note here before we proceed into this that basically 0 semesters of calculus was 55%. 1 semester was 32%. And what does that leave us with? 13%. So 2 or more semesters is 13%. Just for reference so that I don't have to keep looking back. So 2 or more semesters of calculus. That would imply that I need to, this technically, I've already found this number, but 2 or more semesters of calculus, we would have to, technically mathematically, what we did to find this was say 100 minus the 55% that don't have any, minus the 32% that don't have, or only have 1, and that's what would give us that 13%. So we kind of did that by writing that in, but anyways, that happened to answer part A. All right, what about some calculus? What do you think that means?
1 semester. Or really add like this 1 semester and 2 semesters.
Yep. So anything, so basically they have any amount of calculus. So 1, 2, infinity, whatever. So essentially it's everything but the no semesters. So we'll take that and add it up. So this means 1 or more semesters. And this is one where sometimes we would use the complement, and this one it's pretty easy. We don't really need to use the complement, but later on in some other examples we will. So 32%, or 32 plus 13, so 45%. And obviously if we want to make these true probabilities, because probabilities aren't percents, we would say 0.13, 0.45. But since they gave us stuff in percents, I kind of just left it in percents. All right, what about no more than 1 semester? What values would that imply I'm dealing with?
1 semester and no calculus.
Yep. So basically 0 or 1 semesters. So that would be 55 plus 32, which would be 87%, or if we wanted it as a probability, 0.87. Bless you. All right, probability of repeated events. If 2 events, A and B, are independent, which means the outcome of A does not change the probability of B, then the probability of both occurring is the probability of A union B, and remember union represents or, so we could say either thing, probability of A or B, probability of A union B, but the technical symbol is what I have written here, is equal to the probability of A plus the probability of B. In the next, I want to say it's the next chapter, is where we have one if they are not independent events, and how that looks. But for right now, if they are independent, then this is our formula. So, example 4 is going to refer back to 3. So you are assigned to be a part of a group of 3 students from the intro stats class described in example 3. What is the probability that of your other 2 group mates, neither has studied calculus? So, does one person studying calculus affect the other? No. So that means that each of those is we're gonna look at the probability of them having no calculus. So that's gonna be 0.55 times 0.55, and that's going to come out to be 0.3025. So that's the probability that neither of them has studied calculus. Probability that both have studied at least 1 semester of calculus, so that would mean I need to add up the basically 32 and 13, so 0.32 plus 0.13 is 0.45, so this is going to be 0.45 times 0.45, which is 0.2025. Now, this last one is where it gets a little bit more tricky, so we're actually going to have a little diagram here that we draw with this one. So, at least one has more than 1 semester of calculus. Okay? So, those are kind of our things here. All right, now, does it matter which person has more than 1? Correct. It doesn't matter. I just have at least one of them has more than 1 semester. They could both have more than 1. Just one of them could. It doesn't matter which person it is. What we're going to do is we're going to draw a little diagram. So more than 1 semester means that they have to have had at least 2, like at least 1 person in the group. So I'm going to do a little diagram here. We're going to do branches up here as well, so just make sure you leave some space. So I'm going to go ahead and draw this, and then we'll write in our numbers that are going on here. All right, so the first person, or the first option for person 1, so that's what this first set of branches is basically I can have either 0 or 1, or I can have 2 or more. Then, once I have that, I'm going to have 2 or more on this one, 0 or 1 here. And then same thing down here, 0 or 1, and then 2 or more. So then when we go through each branch piece to do this mathematically, what we do is we multiply the probability of each thing. So this top one, 2 or more and 2 or more, that is going to be 0.13 times 0.13. And we'll get that number in a second. But we may or may not need to find all the numbers, so I'm just going to write them all. Because sometimes we will need them, sometimes we only need certain things off of it, but we want to have all of our options listed. The next one could be that person 1 has 2 or more, person 2 has 0 or 1. So this is going to be 0.13 times the addition of 0 or 1, which would be 0.87. This next one is the same thing, just this reversed. So 0.87 times 0.13. It's basically person 1 has none, person 2 has 2 or more. Then the last one is that basically like 0 or 1 and 0 or 1. So that is going to be 0.87 times 0.87. But can I have this last situation?
No.
No, because it says that at least one has more than one semester. So I have to have one of the options where there's 2 or more. So there's 2 different ways that I can do this. So I'm going to show you both ways just so that you have it for a reference. So the first way I can do this is I can say, all right, well, in this first scenario up here, both had 2 or more. So I can say, all right, well, that would be 0.13 times 0.13 plus the probability that this first one had 2 or more and the second person had just 0 or 1. And then I have the exact same thing down here. So basically these 2 in the middle are the same thing. They're just written backwards. So I would have 2 times 0.13 times 0.87. And if I do it this way, obviously I don't need to account for this one. So this comes out to be 0.2431. But if we had a problem that was a little bit harder than this one or more pieces involved, we may not want to go about it this way. Because there's only, out of my 4 options here that I have, only one of these is going to cause a problem for what this problem is asking for. So I can perhaps use the complement rule, which would be 1 minus the probability that none had 2 or more semesters. So I could instead just do 1 minus 0.87 times 0.87. And if I did that, I would still get 0.2431. So either way, I'm going to get the same thing. All right, we're going to do example 5, and that's probably where we'll stop for today. I'm going to give you all your tests back also. All right, so this is kind of a long example. So a Pew Research poll in 2007 asked 2020 U.S. adults whether fathers today were doing as good a job fathering as fathers 20 to 30 years ago. Here's how they responded. So basically 424 said that fathers today are better. 566 said that they're the same. 950 said that they're worse, and 80 had no opinion. So if we select a respondent at random from this sample of 2020 adults, what is the probability that the selected person responded worse? So we take the number that said worse, so 950, and we divide that by the total number, which is 2020. So 950.
I thought that was a year.
Yeah, the first time I did this, it was like, I think the first time I actually taught this chapter was like in 2020, and I was like,
Where did they get that?
that's weird. I was like, that's really ironic because this book is older than that. Okay. So 950 divided by 2020, and we would get 0.47 for that. So that's the probability of that.
Did you just like add a comma?
Yeah. It would make it so much easier. But also I think it would be less confusing if we weren't in 2024.
Yeah.
And all the PTSD of 2020. What is the probability that the person responded same or better? Okay, so obviously they couldn't respond both ways, so they had to choose one, so better or the same. So we add those two things together because they're independent, and we're going to divide that by 2020. So we're going to have, not 950, 424 plus 566 over 2020. And so that ends up giving me, just if you're wondering, 990 over 2020. And so that gives me a probability of 0.49. So notice this was just basically saying if we pulled one person, what are we going to get? So now in C and D, if we selected two people at random, or I guess maybe for the rest of these, if we selected two people at random from this sample, what is the probability that both think fathers are better today? So the difference with this problem and the last one that we had was the last one already gave us 55% had no calculus, or whatever the number was. These ones, they've just told us a quantity of people that have said better, same, worse, no opinion, and they've given us a total number. So we don't have percentages. So we're going to have to basically make the decimals ourselves. So the first person's independent of the second one, so we're going to be multiplying them. So both are better today, so 424 out of 2020, so that's person one, times person two thinks the same way, 424 out of 2020. And if I do that, I would get 0.04 for the probability of that one. Now, because these both were thinking the same way, the other thing, or the other way I could have written this would have been 424 out of 2020, and I could have squared that, which is essentially what I did when I typed into my calculator, because that means the exact same thing. So if they're both saying the same thing, you can just square the number. So then in D, what is the probability that neither thinks fathers are better today? Any idea about this one?
Are we adding same, worse, and no opinion? And taking that out or no?
Yeah. So, good catch. Because it just says that neither thinks that they're better. So they could be the same, worse, or they could have no opinion. So what I would do is use the complement. So I'm going to have on top 2020 minus the ones that think better, so 424, out of the total number, which is 2020. So on the top, I've done the complement rule for basically 1 minus that they think it's better. Obviously, it's not 1 minus, but that concept. We take the total and we subtract off that amount. Now, both thinks this way, or, well, neither think, whatever, however you want to say it. So we can just take that number and square it. This comes out to give us, let's see, 2020 20 minus 424 is 1596 out of 2020. And we can square that number, or we can write it twice, however you want to do it. So divided by 2020, square the number. So this gives me a probability of 0.62. So then, this next one, what is the probability that one person thinks fathers are better today and the other doesn't? Order doesn't matter. It doesn't matter if the first person thinks they're better and the second person doesn't, vice versa. So, that they are better would be 424 out of 2020 times that they are not. We can just use this because we've already found this up here, this 1596 over 2020. So multiply those things together. Now, because it doesn't matter which way this can happen, I need to multiply this by 2. Because there's 2 different ways that this can occur. So I'm going to take and multiply this whole thing by 2. Because the first one could say that they're better, and the second one say they're not. Or the first one could say that they're not, and the second one could say that they're better. So that's why we're multiplying this one by 2. Make a note here. Multiply by 2, because there are 2 ways this can happen. So I've got 424 divided by 2020 times 1596 divided by 2020, and then times 2. So this would give me 0.33. So that would be my probability on that one. Alright, so no more math in these last 2 questions, but what assumption did we make in computing these probabilities? Basically about the people from C through E.
You're more likely to have people who think that fathers aren't better than ones that are better.
So that might be true, but that didn't change how we made it, what assumption we made about these probabilities. So did one person affect the other? Did me saying that they're better affect your answer of saying what you thought? No. What was the word I kept using over and over again? Yes. So basically the probability responses are independent. Explain why you think that assumption is reasonable. So, just because I want to be able to give you all your tests back. They are chosen at random, because it was a poll. And then basically one person doesn't affect the other. All right, so we will pick up